Okay, good evening, everyone. Homework number 1 has been posted. Right, so there are five problems, 5 or 6. Right, 5, and it will be due 30th this month. Right, so 2 weeks. Still, you have 2 weeks. But it must be paper. Okay, so not electronic, paper-based, and bring the hard copy to the class on 30th October. Okay, it needs to be hard copy so that we can return the graded homework to you, more easy way. Okay, easy way. All right. So today is our last lecture on water treatment. Okay. So in previous lectures, we focused on suspended solids, right? Particles. So for example, last lecture, what do we have covered? Membrane separation, right? Membrane separation. But membrane separation, we know membrane separation is effective in biological control, right? Control of waterborne pathogens, but it is still very expensive. So in most of places, we're still using sand filtration, right? Sand filtration. And through sand filtration, we can remove a significant portion of the waterborne pathogens, but still not 100%, right? So not 100%. But waterborne pathogens are high risk, right? High risk. Sometimes it's immediate effect, right? When we discuss chemical pollution could be chronic, right? Chronic. It could take, for example, years for someone to develop a symptom, right? So control of pathogen is very, very important requirement in our water treatment. Okay, because you drink. Actually, not only in water treatment, but also wastewater treatment. If you go to look at the wastewater treatment process trend, typically at the end there is a disinfection step. Okay, disinfection step. So why do we care about pathogens? Let's first look at a number of water-related diseases. Okay, diseases. The first one is typhoid fever. Right, it's an illness caused by the bacterium Salmonella typhi, and it's transmitted by ingesting a food or water contaminated with feces from an infected person. So here we see that sanitation is also important. Sanitation is part of the clean water scheme. Clean water scheme. The worst year was 1891 when the typhoid death rate was 174 per 100,000 people. Right. So this is one type, typhoid fever, but we have some other water-related diseases. They are caused by different pathogens. Second major disease, right? Cholera occurs through ingesting food or water which is contaminated with Vibrio cholerae. In most severe forms, cholera is one of the most rapidly fatal illnesses known. Right? So it's a fatal disease. Okay. Right. You see major outbreaks in the 19th century. Right. In the 19th century. So why? Over 100 years ago. Because in early 20th century, disinfection using chlorine was invented. Right. So since then, we did not see this type of major outbreak. Okay, major outbreak. So what we will cover today: introduction to disinfection, its history, objective and methods, and we discuss disinfection kinetics, especially a very important concept, the CT value, concentration times contact time, right? CT value, and we also go through a number of common disinfectants, discuss their chemistry, free chlorine, combined chlorine, ozone, chlorine dioxide, and UV, right? UV, of course, it's high energy UV, UVC, and their advantages and disadvantages. Okay, and finally some design parameters for disinfection tank. Right, so here we're talking about control of microbial growth. There are a number of ways, right? A number of ways. What are they? So what can you think of? So why we drink hot water? Why drink hot water? What are the methods to inactivate microorganisms? Heating, right? What else? What are the methods? So how can you kill bacteria? Heating. How about some chemicals? Something everybody likes. Silver. All right. You could also use copper, which is cheaper. All right. So we can use chemicals. These are metals. We have some other chemicals which can perform the inactivation. Right. So these chemicals are typically oxidants, and very strong oxidants. Right. And we have different ways to control microbial growth. The first one we call sterilization. Destroys or inactivates all forms of organisms. Sterilization. So what do we do? Autoclave, right? Autoclave. In our laboratory, if we want to do some microbial experiments, we need to sterilize our glassware, right? In that case, it destroys all forms of organisms, sterilization. And sanitizer, hand washing solution, right? Sanitizer, or you call sanitizing solution. Chemical agent that reduces the numbers of organisms to safe levels, right? So in our wastewater, we have a portion, some concentration of sanitizer, right? Imagine if you wash your hand, where is the wastewater, right? So it goes to the wastewater treatment plant. Sanitizer, bacteria stat, chemical agent that prevents microbial growth but does not kill them. Okay, prevent growth. And disinfectant, physical or chemical agent that destroys or inactivates disease-causing organism. Disease-causing organism, we call them pathogens. Okay, pathogens, but not all microorganisms. That's disinfection. So disinfection methods, as I mentioned, we can use chemicals, oxidizing substances are the most common, and metals such as silver, copper, right, and zinc as well. Acids and bases. Right. So what kind of acids? What kind of acids? Hydrogen chloride. But we do not use that very often in our daily life, right? We use acetic acid sometimes. Acetic acid. Acetic. So please check. Acetic acid. CH3COOH. Acetic acid. Surfactant. And physical, we can use heat. And mechanical, sedimentation, filtration, membrane separation, absorption. And radiation, light energy, right? Light energy. Most common is UV. So in our daily life, we may see UVA. So UVA, UVB, UVC corresponds to different wavelength, right? Wavelength. And X-ray, even higher energy, right? Even higher energy. History of disinfection, right? Asian civilization, like in Egypt and China, right? We use filtration or use coagulation, right? In India, heat foul water by boiling, right? Roman Empire, right? Mildly disinfection by sunlight, okay? By sunlight. And 1850, John Slow, right? One of the first known users of chlorine for water disinfection. So attempted to disinfect the Broad Street pump water supply in London after an outbreak of cholera. Right? It was experimented as early as in the middle of 19th century, disinfection. 1897, right? Still in England, public approval for the use of chlorine for disinfection. It began to be used in large scale. So, right, this is our purpose, objective: inactivate pathogenic organisms. So we consider some indicator organisms such as E. coli, right? And Cryptosporidium oocyst and Giardia cysts and protozoan, all this. Right. So if you go to look at the drinking water standard, right, it will show you what kind of pathogens should be tested. Okay, tested. But we can imagine in water you could have so many types. So we are measuring the indicator organisms. Okay, indicator organisms, but they are also very dangerous. Very dangerous. Surface water treatment rule: 3-log reduction of Giardia. What is 3-log? 99.9. Right. So 1-log is 90%, 2-log is 99%, 3-log is 99.9, and 4-log reduction of entering viruses, right? 99.999%. And we need to maintain a small concentration of residue disinfectant in the water distribution system. Right. So typically 0.2 milligram per liter. 0.2 milligram. Right. What is the purpose of this residue chlorine? To control microbial growth or regrowth in the water distribution system. Right. There are two kinds of disinfection. Primary disinfection achieves desired level of microorganism kill or inactivation. Primary happens in water treatment plant. Okay. And there's secondary disinfection, maintains the disinfectant residue in the water distribution system. Okay. In the finished water. Okay. So we add certain concentration before the water goes out. Okay. Not very high. Right. This is a treatment process trend. I just want to refresh your memory again. Our process trend, right? Screening, coagulation, fluctuations, sedimentation, sand filtration, and then disinfection, and storage, and then distribution. Right. So each topic, one lecture. Right. So the biofilm is very nasty, as we discussed in membrane separation, right? Biofouling. Microorganisms grow in the pipes as well. Okay, pipes as well, like this. Okay, and once they have grown on the surface, it becomes very difficult for you to remove. Okay. So we add certain low concentration of disinfectant in water. So what do we desire for a good disinfectant? Can you imagine? Non-toxic, right? Non-toxic, effective, cheap. What else? fast. Okay. What else? Destroy pathogens, including bacteria, virus, and cysts. Right. So it needs to be a wide spectrum, targeting bacteria, virus, and cysts, because this microorganism have different structures, right? Structures. So one method could work for certain microorganism, but fail to inactivate other microorganism. That could happen for certain methods, right? But for a popular one, it needs to target wide spectrum of microorganisms or wide spectrum of pathogens, to be more specific, and works effectively over a wide variety of water quality conditions. This is also very important. Okay. We're not having a lab session, but if you do the chlorine experiment, disinfecting experiment, you will see that substances in water could consume certain portion of your added chlorine, right? So that is interference. And the disinfectant needs to overcome that interference to become more effective and non-toxic. Okay, so this is evident, right? Evident, inexpensive, safe, and easy to handle. Right? So here, hydrogen peroxide, right? Hydrogen peroxide is a disinfectant, oxidant, right? But we did not say this in wide use in water treatment plant. Right? It's not safe. It's very expensive. Okay? And available methods determine concentration, measurement, because you want your water quality to be stable. So you add the same concentration, right? And you measure its change, and you control that every time. And persistent, provides residue to prevent regrowth of microorganisms. Right? Persistent. So we are utilizing here oxidants. Right, these are the powerful oxidants. So disinfectant we typically use, such as ozone, right? Ozone, but not hydrogen peroxide. Hydrogen peroxide only in small scale, right? Small scale. And permanganate. Okay, permanganate. This is used in certain water treatment plant. Okay, chlorine dioxide, hypochlorous acid, chlorine, right? So these are chlorine-based disinfectant. Hydroxy radical, very strong oxidant. It is very short-lived, right? So in millisecond, its lifetime millisecond. So very short-lived, but very powerful. Some research is going on, but the major purpose is not to inactive pathogen, but to degrade contaminants, chemical contaminants. Hydroxy radical. So common disinfectants include chlorine compounds. Chlorine compounds can be used in liquid, gas, solution, or solid form. Right? So this is a gas form. Chloramine. Right? So what is amine? NH3. Right? NH3. And one hydrogen is replaced by one chlorine atom, formed by addition of ammonium and chlorine gas to the water. Right? Later we'll see the reason why we produce chloramine. Okay, so why we make this chemical and use it for disinfectant. And ozone, chlorine dioxide, and UV. Factors affecting disinfection, the pathogen themselves, right? Pathogens themselves, and then water quality, turbidity. Particulates can shield microorganisms. What does shield mean? So they can prevent the reaction between your disinfectant and pathogen, right? Natural organic matter, NOM, right? NOM exert disinfectant demand because NOM reacts with disinfectant. Okay, NOM is a very, very hot topic, popular topic. Right? So there are many, perhaps thousands of papers published every year on this topic, reaction of NOM and different disinfectants, leading to DBP formation, disinfection byproduct. Okay, we will see what kind of DBPs and what are the adverse effects of DBP. And pH, right? pH may change the form of disinfectant. For example, hypochlorous acid versus hypochlorite, right? Later we're going to see that hypochlorous acid is much more powerful than hypochlorite. Right? The pH is also important. And temperature, right? Mass transfer. Temperature could affect mass transfer. So generally speaking, higher temperature, faster transport, right? Faster transport. And K design variables, disinfectant concentration times contact time, C times T, and this is CT value. Okay, CT value is a design variable we use. Concentration times time. Disinfection kinetics. First model is Chick's law. Right? Neutralizing microbiological activity can be compared to a chemical reaction. So here N is a microorganism concentration, right? dN over dt is change of the concentration over time. And K is the rate constant. Okay, rate constant depends on disinfectant type and concentration, organism, and temperature. So K is the rate constant. What is this? This is the first order reaction kinetics, right? You don't know? First order. No one knows. What is first order? What is zeroth order? dn over dt equals minus k. What is this? Zeroth, right? Because if you write n here, it's n to the 0, right? dn over dt equals minus k n to the 1, first order kinetics, right? We have second order as well. So here it's first order reaction kinetics. And we can transform the equation and we get this, and this is very typical. Right? And this is the transformation, first order, right? Transformation. So what do you get here? Basically, if you measure microorganism concentration and time 0, you get n naught, right? And at time t, you measure concentration, you get n. And if you plot natural log of this number with time, you get a straight line, which is k, right? Which is k. Confused? This is a mathematical treatment, okay? First order reaction k is a first order rate constant. First order rate constant. And this is half time, half-life. Half-life, when the concentration is reduced to half of the initial value, right? The time it takes is half-life. The second model is Watson's law, right? Watson's law. Diffraction is a function of disinfection concentration. If we write Watson's law, say to the nth power times t is constant and is a function of disinfection agent. When n is smaller than 1, contact time t is more important than concentration. But when n is larger 1, the efficiency decreases with dilution. The concentration here is more important. Okay. And if we combine these two, right, Chick's law and Watson's law, we got Chick-Watson model. It relates the rate constant of inactivation k to the disinfectant concentration. Right. If we write down this, k star equals k times c to the n. And the coefficient of dilution, a weighting factor, can be assumed as 1. If we write this equation, we get this. Right. Natural log n to the n naught equals minus k times c to the nth power times t. And therefore, there is a C versus T trade-offs. C versus T trade-off. Right. So this is one example. The y-axis is E. coli survival, and x-axis is contact time. The contact time means what? What is contact time? So literally, the contact time between disinfectant and microorganism, right? In reality, what is that? It's HRT, hydraulic retention time, right? Because disinfection happens in a tank, right? It continuous flow. It continuous flow. So contact time is the amount of time for water to stay in that disinfection tank, right? So contact time is actually hydraulic retention time. How much time the water spends in a disinfection tank. Okay, and we have different concentration, 0.05, 0.07, 0.14. Right? To achieve the same amount of inactivation, if you use higher concentration of disinfectant, you just need shorter time, right? Shorter time. We compare the same level, right? So here is how much time you need. Here is how much time you need when you apply 0.05 milligram per liter of chlorine. And suggests a nonlinear relationship between C and T. Right? So the city concept, disinfection activity can be expressed as the product of disinfection concentration and contact time, C times T. C times T. Right? So based on Chick-Watson law, disinfectant concentration and contact time have the same weight or contribution in the rate of inactivation and in contributing to CT. What does it mean? The same CT values will achieve the same amount of inactivation. Okay. So if you keep the water in the tank longer, you can use a lower concentration of disinfectant, right? But if you want to achieve faster inactivation, you just increase the disinfectant concentration. Okay. Does it make sense? So that is based on Chick-Watson law, CT value. All right. So this is a very simple example. Pay attention to the unit, milligram per liter times minute. Okay. Minute is a unit of time. So CT value is 100 milligram per liter minutes, right? If your concentration is 1 milligram per liter, then T must be 100 minutes. So CT value is 100. Concentration increased to 10, then you just need 10 minutes. Right? If 100 milligram per liter, which is very high concentration, you just need 1 minute. Okay. So any combination of C and T giving a product of 100 is acceptable. Okay, because C and T are interchangeable. CT value is a function of organism, disinfectant type, pH, and temperature. Right. Right. Look at this table. CT values for inactivation of Giardia sites by free chlorine at 10 degrees Celsius. What variables we have here? pH. Right. We have pH. We have chlorine concentration. We have contact time. Oh, sorry. We have log removal. We have then the required CT value. CT value. Okay. For example, if our water has a pH of 7, we want to achieve say 2 log removal. 2 log removal. Right. And then you need to look at the chlorine concentration. Right. You need a different CT value. Okay. So any pH relationship. If we increase the pH to achieve the same log removal, we need a lower or higher CT value. Increase the pH. Lower or higher? Higher? Lower? Read the table. Increase the pH, the same log removal. Higher, right? Larger. A larger CT value. Why? It means under higher pH, the disinfection power decreases, right? Decreases. Why? Acid. Acid is more powerful than hypochlorite, right? So we need to actually understand what is free chlorine. What is the composition of free chlorine, right? Under different pH, the composition changes. And that changes the disinfection power, which we will discuss later. Right, so let's do one example before we take a break. Size a chlorine contact tank for treated water flow of 100 cubic meter per day. What is this? Q, right? Flow rate Q. pH 7, temperature 10 degrees Celsius. Assume chlorine concentration in the tank is uniformly 2 milligram per liter. Right, 2 milligram per liter. You're asked to determine the volume of the contact tank. And what is your removal target? What do you need to determine the volume? And what is the realistic scenario within your tank? So take a pen. We know Q. We know the concentration. Like we have done in many previous examples, if we want to determine the tank size, what do we need? So what is the equation we typically use? Right, so he said HRT equals V divided by Q, right? So that is the typical equation we use. HRT HRT equals V divided by Q, right? So we want to determine V. That's the equation we use. You know Q already here. So you have to determine HRT. So what is HRT? HRT is contact time, right? Okay. So what is the answer for the first question? What is the target? Hmm. 3 log, right? 3 log of Giardia size. So that is your target, 3 log. And if we want to achieve 3 log at pH 7, 10 degrees Celsius, what is the contact CT value we need? Where should we find the information? CT value. Here, right? The table. Giardia cysts. pH 7, 3 log. What is the concentration? 2. So 124. 124 is the CT value you need to achieve 3 log inactivation of Giardia cysts at 10 degrees Celsius under pH 7. Okay? So first question is 3 log reduction. Then from the table, the CT value we need is 124 milligram per liter minutes. That's the CT value. Then the time, contact time, because the concentration is 2, right? So the time is 124 divided by 2, 62 minutes. That is the contact time. Right? So we said contact time is the HRT, hydraulic retention time. Right? Hydraulic retention time. Q is 100 cubic meter per day. It's given here. Therefore, the V is this. 4.3 cubic meter. 4.3 cubic meter. It's not a very large tank because the flow rate is not large. Okay. Of course, we assume chlorine concentration is uniformly distributed. Okay. But in reality, it may not because there's reaction, consumption, right? Consumption. Okay. Any question regarding this? No? Okay. So let's take a break. If you have not got a step, please read the solution again. Okay, take a break. Okay. Remember this equation, okay? HRT goes V divided by Q when you want to size a tank. Right? So next, let's discuss different types of disinfectant. Okay, different types of disinfectant. The first major type is chlorine, of course, right? Free chlorine. Free chlorine. As you can see from this graph, after its invention, chlorination of water, right? The death rate for typhoid fever substantially decreased. Substantially decreased. Right? So this is one of the most important inventions in the 20th century. Chlorine disinfection. It's very effective. It's very effective, and you can compare all this number, right, at different time. And life expectancy. Life expectancy. Average in the 90s, the early 20th century, lower than 50 years old. But now it's above 75. Above 75, right? So we have the longest life expectancy in Hong Kong, right? Longest in the world. What is the number? Anyone knows the number? 80 something? I forgot the number, but it should be the longest. I remember. 80 something maybe. All right. So chlorine is one of the halogens, right? Fluoride, chloride, and bromine, and iodine. 1825 first used in wastewater treatment in France, and 1917 chlorine amines taken into use in Canada and USA. Right. The chlorine gas, yellow green, very strong characteristic smell. Everyone has the feeling, right? If you go to a swimming pool, that's very obvious for the smell. Very strong oxidizing agent, can be explosive. Poisonous, forms several undesired chlorinated substances. First used in 1905 in London, 1906, 1908 in Chicago, in the USA, followed by dramatic reduction in waterborne disease, has been the disinfectant of choice in the US until recently. Being slowly replaced by alternative disinfectants after discovery of DBP, disinfection byproducts, such as trihalomethanes. What is trihalomethanes? What is methane? CH4. Okay, good. Everyone knows. What is tri? What does tri mean? 3, right? 3 halo. It means, so here, this is methane, right? This is methane. The 3 hydrogen has been replaced by Cl, right? So trihalomethane. So this chemical, right, if you add chlorine in the water may have a trace amount of methane, right? And you have this produced. What's the problem with this? What's the problem with this chemical? It's carcinogenic, right? Carcinogenic. And other chlorinated organics. So in water you have other chemicals which could react with chlorine, because chlorine is very reactive. It's very reactive, right? And these chemicals are called disinfection byproducts, DBPs, right? DBPs. And recommended maximum residue concentration of free chlorine is lower than 5 milligram per liter by US EPA. Okay. And the trend in disinfectant use. This light blue is the year of 2017, and dark blue is 1978. 1978. Look at 1970s. Chlorine gas is the dominant, right? Dominant disinfectant, over 90%. Over 90%. Others account for less than 10%. But how about nowadays? This light blue color. Nowadays, it's less than 30% in the US, chlorine gas, right? So equally important is hypochlorite. So these two combined close to 60%. But we have seen other chloramine, the use of chloramine, and some ozone, some UV, right? Some ozone, some UV. So you can see the trend, a substantial decrease of chlorine gas, substantial decrease, and increase of hypochlorite. And chloramine in the 2000s, that's a peak. And now the usage has been reduced somehow, right? But still free chlorine is a majority. Okay, is a majority. And what is free chlorine? We have chlorine gas, right? And this gas can dissolve in water. And at typical pH, we have hypochlorous acid and hypochlorite ion produced. Okay, so this is this reaction: chlorine gas, water, hypochlorous acid, proton, right, and chloride. And hypochlorous acid, its dissociation produces hypochlorite. And what is free chlorine? Hypochlorous acid plus hypochlorite. That is free chlorine, right? So hypochlorous acid is 10 times more powerful than hypochlorite. Therefore, higher pH, you need more because you have more hypochlorite, right? Look at this speciation of free chlorine. With the increase of pH, especially above 7, hypochlorous ratio substantially decreases, right? Substantially decreases. Okay, so what is free chlorine? I believe that's a question I asked in previous exam. What is free chlorine? And what is the pH relationship? Okay, think about these equations. Okay, sodium hypochlorite and high test hypochlorite also form hypochlorous acid and hypochlorite. Right, this is the equation. We first get hypochlorite, and protonation of this produces hypochlorous acid. hypochlorous acid. So when the pH of the solution is here, there is 50% hypochlorous acid and 50% hypochlorite. Is this statement true or not? True or not? So at this pH, they have the same percentage, equal percentage. True or false? False. Why? Right. So it's false. Why? In addition to this too, you could have other chlorine species, right? Not only this, because chlorine is very reactive. It could react with other substances, forming other chlorinated products. Right. Biocidal efficiency. Okay, pH relationship. Right. Clearly shows hypochlorous acid is more powerful, much more powerful than hypochlorite. Okay. And chlorine demand. Right. So it reacts with inorganic reducing species such as iron 2, manganese 2, hydrogen sulfide. Right. So there will be redox reactions between free chlorine because they are oxidant and these are reducing species. Okay. And the reaction consumes chlorine. And we also have NOM, natural organic matter or dissolved organic carbon. They consume chlorine as well. Okay. They consume chlorine as well. And so we have this breakpoint curve. If you have a water sample, and if you you add free chlorine into the water sample, you measure chlorine concentration in a water sample, you will see this type of curve. Right? First increase, then decrease because of consumption. Okay, because of consumption by the substances, and then it goes up. Okay, because of consumption by these chemicals or natural organic matters in water. And DBP, we have mentioned trihalomethyl here and haloacetic acids. Okay, haloacetic. What is acetic acid? CH3COOH. Right. So here you have 3 hydrogen, which can be replaced by chlorine. Right. NOM and bromide. Okay. So you look at it here. We can produce many types, many types, and these are typically carcinogenic. Right. Low concentration but carcinogenic. So that is a problem with chlorine disinfection. Right. Chlorine disinfection. How can we do to mitigate DBP problem? What we can do? What is the most cost-effective method? Heat. Why use heat? Use heat for what? Right. So we remove the so-called precursors like NOM. We remove these chemicals or compounds before disinfection. Right. Remember, ahead of disinfection, you have other steps: coagulation, fluctuation, sedimentation, silent filtration. Right. So there you try to remove natural organic matter, so that they do not stay until disinfection. So by this way, you can reduce the production of DBP. Okay, so that's free chlorine. Second type is chloramine. Chloramine, the reaction of hypochlorous acid with ammonia forms chloramine. We have monochloramine, mono means 1, right? Dichloramine, di means 2. Trichloramine, tri means 3. 1 chlorine, 2, 3. So these are chloramine, and they're termed combined chlorine. So free chlorine, combined chlorine, or chloramine. Okay, remember these concepts: free, combined. Right, free chlorine, combined chlorine. And why we produce chloramine? They're more persistent, so their lifetime is longer than free chlorine. Okay, lifetime. Therefore, we can use them for secondary disinfection because they stay longer. Imagine how long it takes for the water to transport from water treatment plant to your home. From hours to days, right? So you need persistent chlorine, and that is achieved by chloramine. Okay, chloramine. So why they stay longer compared to free chlorine? Because they are less reactive, right? That's understandable. If they are more reactive, they react, right? They react. So they are less reactive, therefore less effective, less powerful than free chlorine. Disinfection efficiency, if we compare, hypochlorous acid is stronger than hypochlorite, right? Stronger than monochloramine, then dichloramine, and then trichloramine. That is the order. Okay, that is the order. First used in Canada and Denver in the US, become popular in 1930s, right? And this decreased the usage due to ammonia shortage during World War II. Increased the interest due to the discovery of chlorination DBP during the 1970s. Right? But typically we use it for secondary disinfection, but in certain cases used as primary as well. Right? It is less effective than free chlorine, but produces lower DBP concentration. Okay. 2 different methods of application is preformed. So we produce chloramine first, mix hypochlorite and ammonia chloride, or we can use it through dynamic chloronal amination. Right? Initial free chlorine addition followed by ammonia addition. They can be both used for primary and secondary disinfection, where secondary disinfection be more cost effective. Right? So the philosophy here is simple. Right? More powerful, more reactive, higher DBP concentration, because that's a result of their high reactivity. Okay, so if you reduce the reactivity, you get lower DBP. Right. So this one is very interesting. You compare the CT values for the inactivation of Giardia, and this one is for 3-log removal. 3-log removal, we have free chlorine, we have chloramine. So how about CT value? Free chlorine, you need smaller CT value, right? Compared to chloramine. For example, 10 degrees Celsius. This is 1700. This is only 130. 130, which means free chlorine is at least 10 times more powerful than chloramine, right? When you compare the CT value. So how about ozone? Is ozone powerful from the table? Tell me, is ozone powerful as a disinfectant? Yes or no? How many say yes? Would you raise your hand? No one. How many say no? Still no one. So ozone, the CT value is very small. It means it's very powerful, right? Very powerful. Look at chlorine dioxide. Chlorine dioxide. It's also very powerful, right? CT value very small, right? Did you get my point here? Okay, compare CT value to achieve same 3-log removal of Giardia. Smaller CT value, the more powerful the disinfectant. Right? So chloramines, pros and cons. Advantages: less corrosive, less reactive, less toxic, and chemical hazards. Relatively tolerable to inorganic and organic loads. No known formation of DBP. Right. So currently we don't know. We haven't measured, so we think it's safe. But there could be some DBP produced, but we cannot measure using our current technologies. Right. So we say no known formation of DBP. It's not no formation of DBP. No known formation of DBP. Okay. Can you see the difference? Can you see the difference? No known formation and no formation. It's very different. Okay. Relatively long-lasting residues. Disadvantage: not so effective against virus, protozoan, and bacterial spores. Okay. So for this virus protozoan, you have to use high power disinfectant. Right. Chlorination. Free chlorine is very efficient at killing bacteria. 1 milligram per liter and less than 30 minutes is generally sufficient to kill. Right. Low concentration, very fast. The presence of interference substances in water reduces the killing efficiency, like NOM. Right. The need to boost chlorine concentration to 20 to 40 milligram per liter. So the interference is significant. Significant. Look at the increase, 20 to 40 milligram per liter. All right. Pros and cons. It is a very mature technology, over 100 years, right? So almost 200 years if you count that starting time in 1850. Works quickly, right? Because it's very reactive, easy to measure chlorine. Right? So we have chemical methods, calorimetric, and we have now electrochemical sensor, right, to automatically measure chlorine concentration in water. Good residue effect and overall good economics. So relatively cheap. And cons: taste and odor problems. Right? It is very easy to distinguish the smell of chlorine gas, chlorine. Corrosive, right? DBP problem. The interference from substances in water, and the gas is poisonous, so it could be dangerous for the operation. How we design a disinfection tank? We have seen an example, right? Tank. So typically 3 general types: plug flow, right? So you can make use of compartments and baffles. Serpentine tank. Right. So the flow is in a serpentine pattern. Over and under baffled contactor and pipeline. You have some pictures here. Right. So this serpentine tank, what does serpentine mean? Right. So this is the serpentine pattern. And current is injected here, and we have sensor, and we have sulfide diffuser. What's this? What is sulfide? What is sulfide? Sulfide is added to reduce chlorine to levels that will not cause consumer reaction. Okay. Sulfide is a dechlorination agent. You add sulfide to react the additional current. Okay, so here comes our second practice problem. Water treatment plant use chlorine to disinfect water. After disinfection, the water is dechlorinated using sulfur dioxide, SO2, via the following reaction. You have chlorine gas, sulfur dioxide, right? So you could get chloride and sulfate and some proton. If the concentration of chlorine in water after disinfection is 1 milligram per liter, how much SO2 is required to treat 2 million gallon water? It's very easy, just based on this equation. Reaction. 8 minutes. Easy, right? Of course, you have to change 2 million gallons per day into cubic meters per day, right? Cubic meter per day. And gallon here we use, um, it's American, okay? It's not British. 8.1 kilogram per day. Okay. So molecular weight is 71. What is it? 64. Right. You need this much sulfur dioxide to remove all the residue chlorine. Okay. And we have all the homeworks. We have two homeworks, sorry, two homeworks. Please work on that independently first. Okay. Because it's going to be, the exam is going to be like the homework, the same level of difficulty. Okay. And also do all these exercise problems again without looking at the solutions. Right. If you cannot finish the homework, you may have some difficulty in the exam. Homework is already easy, some kind of. Okay. Okay. Let's take a break. There is a typo on this page. Right, it should be NH2Cl, page 33. Okay. Page. Right. So chlorine is still the most popular, right? With free chlorine, with combined chlorine. And what is the next type? Ozone. It's free chlorine combined. Right. So next is ozone. As we have seen the CD value, right? So more biocidal but more expensive than chlorine. Right? Is effective towards Georgia, right? But for ozone, the most dramatic issue is production of bromate. Okay, bromate. If you have bromide in water, right? So this is bromide ion. If you add ozone into water, you will get bromate, right? Bromate, and bromate is carcinogenic, right? Carcinogenic. So that limits the application of ozone. If you have water containing bromide, you cannot use ozone for disinfection. Right? Reacts with NOM to form biodegradable DOC, including carboxylic acids and aldehydes. But these are not toxic, but they are carbon. Okay, they're carbon. So it must be subsequently biostabilized. And it's both disinfectant and oxidant. Right? We could have chlorine dioxide. Chlorine dioxide. So another type, chlorine dioxide. Okay, but it's more expensive. Okay, we could have then UV, ultraviolet, light irradiation. Chlorine dioxide first used Niagara Falls, 1944, and 1970s used in 84 wastewater water treatment plants, mostly for taste and odor control. Right? And third, DBP were discovered. Right? So you can imagine the industry was seeking other solutions. Right? So they turned to chlorine dioxide. But there was increased concern over its toxicity in 1970s and 1980s, like neurological disorders and anemia, right? By chloride. And maximum combined concentration 0.5 milligram per liter. The relatively low concentration 0.5 milligram per liter. Chlorine dioxide, strong oxidant, good as a primary disinfectant. The reddish yellow gas, very soluble in water, and does not form trihalomethane. Right? Slight taste and odor. Dose limits to 1 milligram per liter due to health concerns. Right? How we produce chlorine dioxide? Chloride plus chlorine. Right? Anyway, some chemistry. Prompts, very effective against all types of microbes. Disadvantages, expensive, unstable. So it must be produced on site. Okay? High toxicity. Like chloride, right? And chloride. These two chemicals are those we want to remove from water. Chloride and chloride. High chemical hazard, highly sensitive organic and inorganic loads, right? Low lasting residues. So basically, it really depends on the condition you want to apply. Right? For different disinfectants, you have to consider multiple factors. Ozone, first used in, so it was very early, 1893 in Netherlands. Right? Early 20th century in the US. Used in more than 1,000 water treatment plants in European countries, but not so popular in the US. Right? Again, increased interest because of discovery of DBP in the chlorination process. Right? An alternative primary disinfectant to free chlorine, strong oxidant, strong microbial activity, perhaps less toxic DBPs. It's a colorless gas, relatively unstable, highly reactive, can oxidize directly or form highly reactive hydroxy radicals. Hydroxy oxide radicals, OH dot. Reacts with itself and with hydroxide in water, hydrogen oxide in water. No THM, trihalomethanes, or any of the chlorinated DBPs form no residue either. Often use a primary disinfectant, followed by chloramine as a secondary disinfectant. Chloramine. Right. Method application generated by passing dry air through high voltage electrodes. So that is ozone generator, and bubble into water to be treated. Right. So this is a ozone generator. Right. We have ambient air containing oxygen. Right. Oxygen into this high voltage electrode. Okay, high voltage. And here we have corona, high voltage corona, converts O2 into O3. Molecular oxygen into ozone. The entire process takes less than 1 second. Okay. This is not very expensive. If you buy a lab scale ozone generator, it costs a few thousand Hong Kong dollars. Okay. And you can produce ozone instantaneous on site. And every disinfecting technology has its advantages and disadvantages. So what are the advantages? Highly effective against all microbes. Right. Disadvantages, expensive comparatively speaking compared to chlorine. Right. Unstable. So it's very difficult for you to transport from one side to another side. It's better for you to produce ozone gas on site. Right? by ozone generator. Highly toxic, right? High chemical hazards. It's very reactive, ozone. Highly sensitive to inorganic and organic loads. Right? It does not form halogenated DBP, but it can form bromate, right? If there is bromide. Okay. So that is the problem with ozone, the formation of bromide. Highly complicated maintenance and operation, and no lasting residue. So you still have to use chloramine as a secondary disinfectant. Okay. So you probably have seen certain news. Okay, certain news about the bottled water. This one, Dasani. I don't know. Is it on sale in Hong Kong? This water? Probably no. Huh? Canada. Okay. Right. So it was found probably containing bromate. Okay, bromate. The Coca-Cola uses ozone for disinfection for the bottled water, but they didn't pay attention to the problem of bromate. In Los Angeles, they have problem with bromate. Okay. So in their water, they have bromide, and they cannot use ozone for disinfection. Right. So it really depends on the source water. Source water. Right. Effectiveness of disinfectants. How we compare? We compare safety value. Right. We compare safety value. Different inactivation. This is for bacteria. This is for virus. This is protozoan. And we have disinfectant: free chlorine, chloramine, chlorine dioxide, and ozone. Right. So ozone has the smallest safety value. Right. Smallest, which shows its power in disinfection. Then chlorine dioxide. That's okay. Look at number. Right. And then free chlorine, and then chloramine. Right. We compare this value. Okay. In a more straightforward manner, hypochlorite, power weak, decomposes slowly. Hypochlorous acid, power strong, decomposes slowly. Molecular amine, the power very weak, but very stable, right? Chloride dioxide, strong, very unstable. Ozone, very strong, very unstable. Okay, so the disinfection power is the opposite, right, of the residue power. Okay, so I hope you could manage this, understand the strength and stability of different disinfectants. Yeah. You should be able to compare them in this way. So which is the strongest? Which is the most stable? Which can be used in primary disinfection? Which can be used in the secondary disinfection? Okay. Finally, physical UV, ultraviolet irradiation. The wavelength 200 to 390 nanometer. Okay. So above that, it's visible, right? Visible range. Artificial UV light mercury lamp developed in 1901. First application drinking water in France, 1910. All these technologies were used for the first time more than 100 years ago. Right. Substantial research on UV in the first half of the 20th century has been used in wastewater disinfection for more than 50 years. Increased interest after the discovery of its remarkable effectiveness against cryptosporidium and Giardia anomalia in the late 1990s. Right. So they're particularly effective for certain type of pathogen. Right. So we have three ranges of UV: UVA, UVB, UVC. Okay. And it's relatively expensive, but it has no residue and no chemical required. And the problem is the depth of light penetration. Right. If your water is turbid, right, you can imagine the effectiveness. Limits the liquid film thickness around each lamp to 50 to 80 millimeter. Light penetration, 5 to 8 centimeter. Therefore, it has limited field application. Okay, limited field application. And in reality, we use UVC. Okay, UVC with a wavelength about 240 nanometer. 240. So very high energy. High energy. What is the mechanism? We have the light, UV light, right? Electromagnetic waves are transferred from UV source to the organism's cellular materials. Right? UV light does not necessarily kill the cell. It activates microorganisms by damaging the DNA or RNA, thereby interfering with replication of the microorganisms. Okay. Damaging nucleic acid. Different microorganisms have different degree of susceptibility to UV radiation depending on the DNA content. Viruses are the most resistant. Virus. Okay, UV. Now some research is going on far UVC, even shorter wavelength. Okay, far UVC. Pros and cons. Right. The pros: no chemicals. Right, no chemicals. So no DBP problem. The light penetration, the efficiency, right, the energy consumption are the cons. Okay, we have some here. Right. So my last slide. It's about disinfection. Safety value, the most important concept of this lecture, and then different types of disinfection methods. Right, disinfection methods. Understand the need, so the objective. objective. And CT value, describe this detailed chemistry of chlorination. So what is free chlorine, right? How do we end up with hypochlorous acid and hypochlorite? And describe pros and cons of other major disinfectants: chloramine, that's combined chlorine, and ozone, chlorous dioxide, and UV. Right? And what are the disinfection power? What are the residue power? Can you rank them? What are the problems with each disinfection method? Right? What's the problem with chlorine disinfection? What's the problem with ozone disinfection? What's the problem with UV disinfection? Right? Right? So it really depends on what kind of application you aim at, and you use that type of disinfection method. Okay? Disinfection is very important. Right. So there are some research going on developing new types of method, like the photocatalyst, right? Photocatalyst. We harvest the energy of the sunlight and use that converging of sunlight to drive certain disinfection process. Okay, so that's it's a very interesting field, and we have so many viruses, so many bacteria, so many pathogens. Some are already there, like Giardia, right? But we have SARS-CoV-2, right? So there's emerging viruses, So what do we do during the COVID disinfection? You know what we do? What do we have used? Still chlorine, right? We use chlorine. We use ozone. Chlorine is most often used in disinfecting the water or wastewater. Ozone is used to disinfect certain surfaces during the COVID. Okay, all right. So that's it. Next week will be a guest lecture. We're still covering lecture 1 of wastewater treatment. Okay. All right. See you next week.